Welcome back to another video lecture on the course Digital Signal Processing. In today's class, we'll continue solving the problems on circular convolution. Good morning, students. Welcome back. Am I audible?
Yes.
Okay. Now let us continue with the problems of circular convolution. In the previous class, last class yesterday, we solved the problems on circular convolution by using two methods. One is a concentric circle method and another is a matrix method. Basically, matrix method is nothing but concentric circle method itself, but instead of representing the sequences on the circumference of the circle, we'll be arranging one of the sequence in terms of the matrix, which represents every row represents one circular folding and one unit shift of that circular folding subsequently. Okay. Now there is one more way of obtaining circular convolution of two sequences, that is by using DFT and IDFT. Okay. Now using DFT and IDFT, to understand this, let us rewrite the statement of the circular convolution. Okay. What does this statement say? If we have two sequences, x1 of n, and if it is n points circularly convolved with the second sequence, x2 of n. Okay, now this is the time domain operation. What should be its equivalent operation in the frequency domain? What should be its n point DFT? Their respective DFTs will be multiplied together. If x1 of k is n point DFT of the sequence x1 of n, and x2 of k is the n point DFT of the second sequence x2 of n, if we perform circular convolution between these two sequences, then their respective DFTs will be multiplied. Okay. Now, while deriving the expression for circular convolution, we consider this product, or we name that product to be x3 of k. Okay. Now, what is that circular convolution? Circular convolution will be nothing but a sequence itself. And in the previous base problem, we denoted that sequence as x3 of m. Okay. Now, how to obtain x3 of m from x3 of k? How to obtain x3 of m from x3 of k? x3 of k is an n point product DFT. If we apply IDFT, inverse discrete Fourier transform, that to n point IDFT on x3 of k, then we will be getting x3 of m. Now this sequence x3 of m will be circular convolution between x1 and x2, but obtained with the help of DFTs. Are you all following? Are you all following? Yes? Is the concept clear? How will we obtain the circular convolution using DFT and IDFT expressions? At least the procedure. Will be solving the problem to understand the calculations. But did you understand what is the flow that will be following? Okay. Now this the operations or the problems what you performed yesterday, both concentric circle method and matrix method, are the time domain approach, because we considered x of 1 and x of 2, the time domain sequences itself. We considered time domain sequences and operated on them, on those time domain sequences. So it was a time domain approach. But using DFT and IDFT, I'll have to convert time domain signal into frequency domain by applying DFT. Operate on those frequency domain signals and then convert it back to time domain. So this is the frequency domain equivalent, frequency domain operation of the circular convolution. So in the problem that we'll be doing, we'll be having two sequences. We'll be considering the same sequences that we considered yesterday for the first problem. We'll have to find their n point DFT, multiply those two, we'll get a product DFT, On this product DFT, you need to apply n point I DFT, which will give us the equivalent circular convolution sequence. Okay. Now let us read the same problem that we did yesterday. Let us consider x1 of n as 2, 1, 2, 1, 4-point sequence, 2, 1, 2, 1. x2 of n 1, 2, 3, 4, another 4-point sequence. Now these two sequences we had considered in the previous class. Okay. So what should be the first step now? What should be the first step? What should be the first step? Who is that? Now this can't be happening every time. Are you all listening? Now for these two 4-point sequences, am I audible? Who wants to answer? Only those students keep your microphone unmute. Rest all mute your microphones. On these two 4-point sequences, you need to apply 4-point DFT. So for the first sequence we will consider. Applying 4-point DFT can be again done in two ways. One by either matrix method or by using the conventional DFT expression. But using DFT is always helpful. It will be more easier compared to the other one. So 4-point DFT or the general expression for n-point DFT using matrix method is capital X of n equals to Wn multiplied by small xn, where Wn is the n cross n twiddle factor matrix and small xn is the discrete time sequence. So for n equals to 4, we will be having 4 DFT points, x of 0 to x of 3. Now for 4 cross 4 twiddle factor matrix, you already have this matrix with you all. You just include them. This will be a 4 cross 4 matrix. First row elements will all be 1. Second row elements will be 1, minus j, minus 1 and plus j. Third row elements will be 1, minus 1, 1, minus 1. And last row elements will be 1 plus j, minus 1, minus j. So this will be a 4 cross 4 twiddle factor matrix which has to be multiplied with the given sequence 2, 1, 2, 1. This will be 4 cross 1 vector. Okay. Multiply these two matrices. So in the first row will be multiplied to the first column. 2 into 1, 2 plus 1 plus 2 plus 1. So the first DFT point will be 6. Okay. Now the second DFT point, to obtain the second DFT point, multiply the second row to this column. 1 into 2, it will be 2. Minus j into 1 will be minus j. Now this time, minus 1 into 2 will be minus 2. So plus 2 in, at the first value and minus 2 will cancel out each other. And last term is j. So this minus j and plus j will cancel out each other. So second DFT point will be 0. Likewise, multiply the third row with this column. It will be 2 minus 1, 1 plus 2, 3, 3 minus 1, 2. Third DFT point will be 2. And likewise, the last one, it will be 2 plus j minus 2 plus 2 minus 2 will cancel and minus j plus j will cancel. So 4 DFT point will also be 0. So 4-point DFT of the sequence 2, 1, 2, 1 is 6, 0, 2 and 0. Okay, so this is the 4-point DFT. So we'll write it here. X1 of t. 4-point DFT of this 4-point sequence is 6, 0, 2, and 0. Okay. Now, for the second sequence, you already have solved this in the first problem. So for sequence 1, 2, 3, and 4. For the second sequence, you multiply again this 4 cross 4 twiddle factor matrix with this sequence. Okay. So first point will be addition of all those samples in a discrete time sequence. So it will be 1 plus 2, 3, 3 plus 3, 6, 6 plus 4, 10. First DFT point will be 10. Okay. Next, for second row, we'll be having 1 into 1, 1, minus 2j, minus j into 2, minus 1 into 3 will be minus 3, and j into 4 will be plus 4j. So we'll be having 1 minus 3, minus 2, and 4j minus 2j plus 2j. So second DFT point will be minus 2 plus 2j. Minus 2 plus 2j. Next, for the third row, it will be 1 minus 2, minus 1, plus 3, 2, 2, minus 4, minus 2. Minus 2 will be the third DFT point, and the last DFT point will be conjugate of the second DFT point, which is minus 2 minus 2j. So 4-point DFT, 4-point DFT of the second sequence. Second sequence is 1, 2, 3, 4. Its 4-point DFT is 10 minus 2 plus 2j minus 2 minus 2 minus 2j. This is 4-point DFT of the second sequence. Am I audible? Okay. Now multiply these two DFTs so that you will get x3 of k, which will be product of x1 of k and x2 of k. Product of x1 of k, x2 of k. Now multiply the corresponding samples in these two DFTs. So first DFT in both the samples will be multiplied. That is 10 into 6, it will be equals to 60. Second DFT point in both of these DFTs will be multiplied. One of the DFT is minus 2 plus 2j, another DFT is 0, so it will be 0. Minus 2 plus 2j multiplied by 0 will be 0. Next, 2 into minus 2, minus 4, and 0 into minus 2 minus 2j will be 0 again. So this is the product DFT, okay, which is x3 of k. Now if you take 4-point IDFT of this product DFT, even though this might be having real values, this is the DFT. This is not a discrete time sequence. Okay, so taking IDFT on this product DFT will give us the circular convolution. That is, small xn is equal to 1 divided by 4 Wn star multiplied by capital Xn. Okay, so this is the formula for inverse discrete Fourier transform using matrix method. 1 by n, Wn star is the conjugate of that twiddle factor matrix, capital Xn is the DFT. So we'll be having a 4-point sequence, small x of 0, x of 1, x of 2, and x of 3 equals to 1 divided by 4. Now write the conjugate matrix. In the conjugate matrix, first row and first columns will all be 1. What will be the second row elements? Second row elements will be 1 plus j minus 1 minus j. Third row elements will be 1 minus 1, 1 minus 1. And last row elements will be 1 minus j minus 1 plus j. So this will be 4 cross 4 conjugate of the Pull factor matrix. This is conjugate multiplied by the 4-point DFT 60 0 minus 4 0. So it will be 1 divided by 4. For now, we'll keep this 1 divided by 4 as it is. Now multiply these two, conjugate of the Pull factor matrix with the 4-point DFT. If you observe, the second and fourth DFT values are 0. So in these values of the Pull factor, wherever there is imaginary value, it will be 0 because it will be multiplied with 0 here. So first value will be 60 minus 4, 56. Second value will be 1 into 60, j into 0, minus 1 into minus 4. So it will be plus 4 and minus j into 0. So it will be 60 plus 4, 64. And likewise, the remaining two values will be again 60 minus 4, 56. And lastly, 60 plus 4, 64. You divide each of these values by 4 now. You will get 14, 16, 14 and 16. This is the idea. So x3 of m is 14, 16, 14 and 16. Is this the same result that you obtained in the first problem? First problem of circular convolution. We had used the same two sequences and the result was 14, 16, 14, 16 itself. Here also it is 14, 16, 14, 16, but this is obtained by using DFT and IDFT method. Did you all understand the procedure? Okay. Now the procedure is very simple. For the sequences given, you need to apply 4-point DFT, multiply the DFTs, you will get a product DFT, and apply IDFT on that product DFT, you will get a discrete time sequence. And this time, this discrete time sequence will be representing the circular convolution. Okay. Any doubts? Any questions? Any doubts? Any questions? Any doubts? Any questions? Okay. Now let's continue. Let's consider one more problem on the circular convolution using DFT and IDFT itself, and then we'll wind up this section. For the next problem, let us define a discrete time sequence as x of n equals to delta n plus 2 delta n minus 2 plus delta n minus 3. Okay. Now what is delta of n? What is delta of n? What delta n is used to represent? Delta n is used to denote delta n is used to represent unit impulse function. Okay. Now the question is, before we find circular convolution and all, How to write a discrete time sequence of it? Okay, discrete time sequence. Writing for a unit impulse expression is simple. Delta n, this impulse will be present at n equals to 0 only, and its magnitude is 1. So first sample in this sequence will be 1. Next, what is this position for the index? Next sample. If this is present at n equals to 0, next sample has to be present at n equals to 1. Okay, for n equals to 1, impulse has to be shifted by one sample, giving us delta n minus 1. But this delta n minus 1 is not present in this series. So, because it is absent, it means the amplitude is 0. Next index will be n equals to 2. For n equals to 2, we have an impulse function delta n minus 2, which will be present at n equals to 2 only. And magnitude for this impulse at n equals to 2 is also 2 because it is multiplied by 2 delta n minus 2. And delta n minus 3, this will be present at n equals to 3 and magnitude is 1. So this is a 4-point sequence, 4-point discrete time sequence 1, 0, 2, 1, which is obtained by these impulse functions. Okay. Now the first question is, find the 4-point DFT of this discrete time sequence. Am I audible? Okay. Now we'll have to find the 4-point DFT of this discrete time sequence. Again, use the matrix method. Capital X of n will be equals to Wn multiplied by small x of n. 4-point DFT, capital X of 0, x of 1, x of 2, and x of 3 will be equals to 1, 1, 1, 1, 1, 1, 1, 1 minus j minus 1 plus j, 1 minus 1, 1 minus 1, 1 plus j minus 1 minus j. For cross 4 25 matrix multiplied by the given signals 1, 0, 2, and 1. So the 4-point DFT will be, first one will be 4. First DFT sample will be 4. Next DFT sample will be 1, 0, minus 2. 1 minus 2 will be minus 1 plus j, because last j will be multiplied to this one. 1 minus 1 plus j will be the second DFT point, and third DFT point will be 1 plus 2, 3 minus 1, 2. 2 will be the third DFT point, and the last DFT point will be 1 minus 1 minus j. Minus 1 minus j. So the 4-point DFT, 4-point DFT of this sequence is 4-point DFT of this 4-point sequence 1, 0, 2, 1 is 4 minus 1 plus j, 2 minus 1 minus j. Okay, this is the 4-point sequence. First part of this question is over now. This is the 4-point DFT of this 4-point sequence 1, 0, 2, 1. Now the second part is, if y of n is a 4-point circular convolution of x of n with itself, find the discrete time sequence y of n. Now the question is, there is a sequence y of n. Okay, now this y of n is circular convolution, n-point circular convolution of x of n with itself. Are you all getting this? There is a 4-point sequence x of n. When that 4-point sequence is circularly convolved with itself, will give us a 4-point another sequence. Now we are calling it as y of n. Now we need to obtain this y of n by using DFT and IDFT method. Now by using DFT and IDFT method, we'll be getting a product DFT y of k, which will be x of k multiplied by x of k. X of k multiplied by X of k will be getting the product DFT Y of k. Apply IDFT on this Y of k, will be getting Y of k. Are you all following? Are you all following? Okay, so multiply X of k with itself. Multiplying X of k with itself will give us the product DFT Y of k. Y of k will be equals to first point. 4 will be multiplied with 4, so it will be 16. Next, minus 2 plus j multiplied with minus 2 plus j itself. Result will be minus 2j. 2 multiplied by 2 will be having 4, and minus 1 minus j multiplied by minus 1 minus j. It will be plus 2j. So this is the product DFT 16 minus 2j 4 plus 2j. Now on this product DFT we will be applying IDFT by using matrix method. Yn equals to 1 divided by e multiplied by the conjugate of this 4 cross 4 middle matrix multiplied by capital Y. Okay, so y of 0, y of 1, y of 2, y of 3 equals to 1 divided by 4, 1, 1 plus j minus 1 minus j, 1 minus 1 minus 1, 1 minus j minus 1 plus j. This is conjugate of 4 cross 4 matrix, which has to be multiplied with the 4-point product sequence DFT 16 minus 2j 4 plus 2j. Okay. Now, let us keep 1 by 4 as it is. So first, when you multiply this first row with this 4-point DFT, you will get 16 minus 2j plus 4 plus 2j. Okay. Likewise, let us write for each one. Next, when we are having 16, j into minus 2j. J into j will be minus 1. Minus 1 multiplied by minus 2 will be plus 2. So we will be getting plus 2. Next, minus 1 into 4, minus 4. And like this, j into j will be minus 1. Minus 1 of this minus will be plus 2. Next, 16 plus 2j plus 4 minus 2j, and lastly 16 j into j will be minus 2 minus 4 and minus 2. So in the first value plus 2j minus 2j will cancel, and in the third value plus 2j minus 2j will cancel. Will remain with 16 plus 4, 20. 20 divided by 4 will be 5. Second value plus 4 minus 4 will cancel. 16 divided by 4, 4. Next, 16 plus 4, 20. 20 divided by 4 will be 5. And lastly, 16 minus 8. So what will it be total? 8 divided by 4 will be 2. So this is the discrete time sequence which will be representing y of n, which will be circular convolution of x of n with itself. Y of n is 5, 4, 5 and 2. 5, 4, 5 and 2. Okay. Did you all understand? Did you all understand? Any doubts, any questions? Now, if you want to verify this result, you can perform circular convolution of this sequence with itself, either by using matrix method or by using concentric circle method. It should result into the same 4-point sequence. Okay, you want to try for that. So with this problem, let us conclude the circular convolution concept. Now let us continue with the additional properties of the DFT. And the next DFT property that we'll be studying is time reversal of the sequence, the sixth DFT property. Time reversal of a sequence. Okay. Now this property states that if x of n and x of k are n-point DFT pairs, then as the name of the property itself indicate, time reversal, time domain sequence will be reversed, and that time reversal in terms of circular nature is represented by x of minus n, x of minus n of capital N. Instead of 4, let us keep it generalized, x of minus n of capital N. Now this minus n represents circular folding. Now circular folding is equivalent to time reversal operation on the circumference of the circle. Okay, which can be represented as, because there will be having n samples, capital N number of samples, and due to the circular symmetry, this time reversal or circular folding x of minus n can also be represented as x of capital N minus small n. X of capital N minus small n means also same, which is x of minus n. Both are circularly folded sequences. Then the question is, what will be its DFT, endpoint DFT? If x of k is the endpoint DFT of the sequence x of n, if we circularly fold this sequence and then take endpoint DFT on it, then what will be the nature of this DFT? Okay, the nature of the DFT will also be circularly folded. Will also be circularly folded and given by x of minus k of n, or it can also be written as capital X of n minus capital X of n minus k. Okay. Now, if you want, at this point of time, you can verify it. Okay. For any one of the 4-point sequence, that is, let's say 1, 2, 3, 4 is a 4-point sequence. You obtained 4-point DFT to it, which was 10 minus 2 plus 2j. Plus 2 minus 2 minus 2j. This was the 4-point DFT, I guess. Then minus 2 plus 2j. Sorry, this is minus 2. Okay, this is minus 2. Now this is x of n and this is its DFT. Now if you circularly fold the sequence, how will you get this? Circular folding, first sample will be as it is, and all the other samples will be reversed. This will be its circular folding. If you plot this on the circle, it will be in the anti-clockwise direction. 1, 2, 3, 4. If you plot its circular folding, then instead of plotting it in the anti-clockwise direction, you will plot it in the clockwise direction. 1, 2, 3, and 4. But how will you read this sequence to write? It will be in the anti-clockwise direction itself. So first sample will be 1, second sample will be 4, next sample will be 3, and next sample will be 2. So this is the circularly folded sequence of 1, 2, 3, 4. Okay. Now if this is the case, what will be its DFT? Its DFT will also be circularly folded. Meaning, first sample will be as it is, and all the other samples will be reversed. Then minus 2 minus 2j, which was last here, it will be here. Minus 2 will be in the same place, and lastly minus 2 plus 2j. Okay. Now compare these two DFTs. How different are they with one another? How different are they? Are you all getting this? Did you all get this point? Did you all get this point? Now, how these two are different? In both of these DFTs, real parts are same. Observe them. 10, minus 2, minus 2, minus 2. In the second sequence also it is 10, minus 2, minus 2, minus 2. Only the imaginary part is reversed. In the first sequence it is plus 2, but in the second sequence it is minus 2. And likewise, in the last sample, here it is minus 2 and here it is plus 2. So, time reversal, circular folding of the DFT will just invert the sign in the imaginary part. The real part will not be affected. We'll be verifying this in DSP lab as well. Okay. Now, this is the overall concept of the time reversal property, and it states that if x of t is n point DFT of the sequence x of n, and if we circularly fold this discrete time sequence, then its DFT will also be circularly folded. That is the property. Now we will have to prove that. Okay. Now to prove, we'll consider this expression. X of minus n, the circular folding, can also be written as x of n minus n. Okay. Now let us apply DFT on this circularly folded sequence. DFT of x of n minus n. DFT of the circularly folded sequence x of n minus n. Now, in the definition of DFT, summation of 0 to n minus 1, what changes do I need to make? The only change will be in the discrete time sequence. Now, instead of x of n, we are taking the DFT of this sequence. This sequence represents circular folding, so it should be inside the summation. X of n minus n e to the power minus g 2 pi k n divided by n. Rest of the things will be as it is. Okay. Now, let us change the index from n to n equals to n minus n. Let us change the index from n to n equals to n minus capital N minus small n. Now, when n is equal to 0, small n is equal to 0, what will be m value? M value will be equals to, if you substitute n equals to 0 here, m value will be equals to capital N. And if n value is n minus 1, which is the upper limit in the summation, then m will be n minus n plus 1. Because of this minus sign, it will be minus n plus 1. So plus n minus n will cancel. So we will begin with 1. Okay. Now we'll be using these here. So DFT of x of n minus n will result into summation. So what will be the lower limit? Lower limit is the summation. M will be equals to lower limit for n equals to 0. M is equal to capital N. So capital N will be the limit in the lower limit in the summation. And when n is equal to n minus 1, the upper limit is 1. Okay. And x of, instead of this n minus n, we have used m. So we'll write it x of m. And in the exponential, e to the power minus j 2 pi k, what will be n equals to that? N will be equals to capital N minus m whole divided by n. This will be the expression. Did you all understand this? Did you all understand this? Okay. Now, observe the limits of these summations. Observe the limit of the summation. How many samples are there in that summation? How many samples? We have n to 1 or 1 to n. Total, how many number of samples will be there? in total there are capital N number of samples. Okay. Now we might be tracing it backwards from N to 1, but in general, total will be having N number of samples. Okay. If you observe the standard definition of the DFT, here also there are N number of samples starting from 0 to N minus 1. Okay. Now, the sequence that we consider x of N minus N is circular in nature with capital N number of samples. Okay. And its corresponding DFT will be periodic with respect to capital N number of samples. That is 0 to N minus 1 are the first period or first set of samples. Next, after N, what will be the next value? Next value will be N, and the next N samples, N minus 1's next value will be N, and the next N samples from N will be 2N minus 1. Yes or no? Yes or no? Okay. Now, because of this periodic nature of the DFT, it doesn't matter from what point to what point you consider. All that matters is the number of samples, number of DFT points what you consider should be equal to capital N. Okay. Now, instead of considering from 0 to N minus 1, I'll consider it from 1 to N. It is safe. Yes or no? So, the limits 1 to N is covering all the samples in the DFT. Okay, and because of that, there is no harm in changing the limits from 1 to N to 0 to N minus 1 because both will be having N number of samples itself. So, rewriting is DFT x of N minus N equals to summation N equals to 0 to N minus 1 this time. Because both of these will be having capital N number of samples itself. X of M e to the power minus j 2 pi k capital N minus N divided by capital N. Is this okay? Okay. Now decompose this exponential. Now this exponential can be written into two exponentials. First one will be e to the power minus j 2 pi k into capital N divided by capital N. And second exponential will be multiplied to minus of this minus will be plus, so it will be plus j 2 pi k into small n divided by capital N. Okay. Now, in the first exponential, n in the numerator and denominator will cancel. Will remain with e to the power minus j 2 pi k. E to the power minus j 2 pi k, and second exponential will be as it is because m is variable. Now, what is the value of this first exponential? In the power, it is integer multiple of 2 pi, so it will be 1 always. Cosine will be 1, sine will be 0. So, in this exponential or that exponential in the expression will be completely reduced to e to the power j 2 pi km divided by capital M, because the other exponential will be 1 always. Okay. Now because of that property itself will be exploiting the same one. Okay. Now because it was 1 in this summation or to this right part of this equation will be multiplied e to the power minus j 2 pi m into capital M. Okay, now what will be the value of this exponential? N is an integer, m is an integer, and this will also be an integer multiple of 2 pi, which will be equals to 1 always. Okay, so multiplying this exponential to this summation will not make any difference to it because we are multiplying it by 1. So we multiply it by e to the power minus j 2 pi m into m. Okay, now combine those two exponentials. Summation m equals to 0 to m minus 1 x of m e to the power. Now, what will you take common? You take e to the power minus j 2 pi m. If you take minus j 2 pi m common, you will remain with n minus k whole divided by n df of x of n minus n e to the power minus j 2 pi m of n minus k divided by n. Now, what is this? Observe the summation on the right hand side. How does it look like? Compare it with the standard DFT equation. How does it look like? In the standard DFT equation, we'll be having the summation, which will be having a number of samples. We have it here. We'll be having a discrete time sequence. We have that here. But instead of the variable k, we have n minus k. So this summation is representing the DFT x of n minus k. It is representing the DFT x of n minus k. Start today. Are you all following? Therefore, DFT of x of n minus k, this circularly folded sequence, is equal to capital X of n minus k, or this will be equivalent to x of minus k. Okay, this means if the sequence is circularly folded, then its DFT will also be circularly folded. If the sequence is circularly folded, its DFT will also be circularly folded. Any doubts, any questions? Any doubts, any questions? Okay. If not, we'll be moving on to the next property that we have to study, and it is called as circular time shift. Circular time shift of a sequence. Circular time shift of a sequence. Okay. And the property states that if x of n is an n-point sequence and its n-point DFT is given by x of k, if x of n is n-point sequence and its DFT is x of k, then as the name itself indicates, circular time shift, time domain sequence has to be shifted, and that time domain shifting, again by the notations that I had written while studying circular symmetries, time shifting or circular time shifting is represented by x of n minus n, x of n minus k or x of n plus k. Now plus k and minus k, they denote the shifting of the sequence on a circle in two different directions. Okay, we'll consider both of them. First for a positive value of n, and next we'll directly write the equation. Whatever we get here, we'll adapt it to for negative value of n. Okay, x of n minus n. This will also be an n-point sequence itself. Okay, we are just shifting x of n on the circle. The total number of samples in the original sequence and the circularly time shifted sequence will be same. There will be n number itself. So if this is x of k is n-point DFT of the sequence x of n, if we circularly shift this sequence, then what will be its DFT? What will be the effect of this circular time shifting on the DFT? And according to the property, DFT x of k will be multiplied by a complex exponential e to the power minus j 2 pi k l divided by n. E to the power minus j 2 pi k l divided by n. So this means if this sequence is circularly shifted, then its DFT will be multiplied by a complex exponential e to the power minus j 2 pi k l divided by n, where L represents the shift by which the sequence is shifted on the circle. Are you all understanding? Okay. This is for today. We'll continue. We'll prove this property in the next class. Any doubts? Any questions for the things that we did today? Okay. If not, hold on. I'll download the